And in part A, we found the velocity of the ball is a function of time given by this, right? The velocity function is just a derivative of the height function, okay, position function. So this tells us the velocity of the ball at each point in time. And then the acceleration is the rate of change of the velocity. And it's a constant minus 32 feet in this case. I was reading, I borrowed this problem from another professor. And I was reading this problem as I put it on the board yesterday. And there's something in this problem that's not quite true. Okay. Has anybody had a physics class in here? Has anybody had physics?
Acceleration can be negative.
No, acceleration can be negative. Yeah. Because acceleration, it instead of saying deceleration, okay, we say negative acceleration in a sense. But the problem is velocity can be positive and it can be negative. And both the velocity and the acceleration are positive, you're speeding up. If both the velocity and the acceleration are negative, you're also speeding up, but you're going in the other direction. So technically it can be negative. The acceleration of gravity, did anybody have physics in high school? Anything? Right? What's the acceleration of gravity?
9.8.
What is it?
9.8.
9.8 what?
Meters per second squared.
Yeah. What is it in feet? It's 32.2 feet per second squared. So we got acceleration in feet, but our units are meters. Okay. So technically, this should have been written. If the units are going to be meters, the acceleration should be 9.8, negative 9.81, right? Or the unit should be in feet. So we got the acceleration of gravity in feet and a problem where the units are in meters. And I was looking at it this morning, I thought, oh, but I mean, it's no big deal, okay, in a sense.
I mean, unless it wasn't thrown on Earth.
I guess you could say that this is a surface of another heavenly body, right? Yeah. All right, so we calculated yesterday when the ball is going upward, and that's during the first 2 seconds. That's after it's thrown upward, and then when the ball has come downward is the next 2 seconds from t equals 2 to t equals 4. So let's move on. So, a diagram of the ball's motion, and this is important to understand this. Okay. Here's the surface of the earth. Okay. And the ball's motion is, it goes up, stops in midair for a second, and then gravity pulls it back downward. So really, the ball just goes up and it goes down. Okay. This is the ball's motion. But you can show the height of the ball by graphing its height function. Okay. And so if you graph its height function, S of t, right? It's a parabola. I'll try to draw this halfway decent. Parabolas are symmetric. Okay. And so this is the graph of its height function, okay? But this is not the ball's flight path. That's what's important for you to understand, right? Because we'll often work with this graph, but the actual ball's motion is to go straight up and then come straight down, okay? If you guys ever take a physics class, okay? Or if you ever, I mean, I'm not saying this sarcastically, I'm sorry. But if you ever take a physics class and you shoot a projectile at an angle, okay? So this one was shot at what, 64, what's this velocity at, 64 miles per hour. That's not its vertical speed, right? You have to break down the, you gotta break down the speed into a horizontal component and a vertical component, right? Using cosine and sine. So, but the implication here is the ball will go straight up, come down, goes back down, okay? Because of the acceleration of gravity. All right. All right, so in D, we want to know when is the ball's velocity increasing. Okay. All right, so a couple different approaches for this, right? Because right, the ball's velocity is increasing, right? It's speeding up, right? Not slowing down. And so one approach that I took was to graph the velocity function, okay? And the graph of the velocity function, you know, is just a straight line, right? This is linear, right? The velocity at t equals 0 is 64, and then it crosses the t-axis at t equals 2. The velocity is 0, right? T equals 2. V of 0 is equal to 64, and v of 2 is equal to 0. Okay. And what's the velocity at 4 seconds? It's minus 64. So it goes from what are meters per second going up to minus 64 meters per second when it hits the ground. So if we graph that, right, that's the graph of the velocity function, okay, as a function of time. And you can see that from t equals 0 to t equals 2, the velocity goes from 64 meters per second to 0 meters per second. I got that written over here. So this is when the velocity of the ball is slowing down because it's going up. And then as it comes down, the velocity of the ball goes from 0 meters per second to minus 64. Right? Negative means it's coming down. Speeding up. Okay. So, when is the ball's velocity increasing? From 2 to 4 seconds, in a nutshell. Any questions on that? So you can graph the velocity function, or you could, right, that's the easiest way probably, just to graph the velocity function, see where the graph is. See where the velocity is changing, right? It's going from a high of 64 to 0, and then from 0 to minus 64 means it's speeding up as well, but the ball is falling towards 0.
Wait, why does that mean it's speeding up?
What?
Why does it mean it's speeding up?
Because going from It starts off here at ground level at 64 miles per hour. When it gets up to here, it's going 0 miles per hour. And then when it goes from here to here, it goes from 0 miles per hour to a negative 64 miles per hour because it's going down. Velocity, the sign of the velocity tells you what direction the object is going. Okay. All right. Input, yes, sir.
At 2 seconds, is it like technically not speeding up or slowing down now? Is that still?
Yeah, because it's hanging in midair,
Right.
right? At some point, it's just going, gravity causes it to stop climbing, and then it plummets towards the earth.
Right.
So, okay. Does that make sense, or?
Between 2 and 4, not equal to though.
Yeah.
Yeah, it's right, it's not less than or equal to, it's just less than. Okay. And at 4 seconds, it crashes into the earth. All right. All right. Another, I'm gonna put a table. I'm gonna address, I think Julianne's question. Maybe it was yours, I can't remember. About the relationship between velocity and acceleration. I'm gonna put that in a table. So I got a 2x2 table, okay? So up here we're gonna have velocity, and over here we're gonna have acceleration. Okay. Now, the velocity can be positive, or it can be negative. Right? And the same is with acceleration. It can be positive, or it can be negative. Okay. So when both the velocity and the acceleration are positive, right? They're both acting in the same direction, and that means you're speeding up. It's kind of like being in your car and you hit the gas pedal. Okay. Both the acceleration and velocity are the same direction. Now, if both the velocity and acceleration are negative, you're still speeding up. So when if we're talking about going horizontally, if the velocity is positive and the acceleration is positive, right, you're moving to the right, and if the acceleration is positive, you're speeding up as you move to the right. If on the other hand, if the velocity is negative, you're moving to the left, and if the acceleration is negative, you're still speeding up, but you're going to the left versus the right. Okay. So when the acceleration and the velocity have the same sign, you're speeding up, but if the velocity is positive, you're going in one direction, and the velocity is negative, you're going in the other direction. If the velocity is negative and the acceleration is positive, you're slowing down. The accelerations were, so we would probably call that deceleration. Right? Velocity is negative, so you're moving to the left, but acceleration's working against you, so you're slowing down as you move to the left. If the velocity is positive and the acceleration is negative, you're slowing down still. Velocity is positive, you're moving to the right, but the acceleration's working against you, so it's like slowing down in the car. And the acceleration's working against you, right? So you slow down. So if the velocity and acceleration are the same, are both positive or both negative, then you're speeding up. If they're of opposite signs, you're slowing down. Okay. speed versus velocity. Right, velocity can be positive or negative, but speed is always positive, okay? So the speed of an object is just equal to the absolute value of its velocity, and which is just the absolute value of the velocity function, okay? We never talk about going to negative, right? How fast were you going on I-95? You never said you were going at negative 70 miles an hour, right? Just say 70 regardless of the direction. So here's the graph. Of the ball speed. Okay, I just erased the graph of the velocity function. Put it back up. Here's minus 60, here's 64. Here's the origin. Here's minus 64. 4 seconds. So that's the graph of the velocity function. And so the graph of the ball speed is the absolute value of this function. So where VFT is above the x-axis, this is the t-axis, I'm sorry. Where the velocity function is above the t-axis, that stays the same. Where the velocity function is below the t-axis, it gets flipped above the t-axis. Okay. So, the graph of the ball speed, which is the absolute value of its velocity function. Here's 64. Here's t equals 2. T equals 4. That's what the graph of the ball speed looks like. Okay. And now you can see from the graph of the ball speed, from t equals 0 to t equals 2, right? The ball is slowing down, and from t equals 2 to 4, the ball is speeding up. Okay. So looking at the ball's graph of the ball speed is also an alternative way of determining when the ball is slowing down and when it's speeding up. Okay. All right, any questions on that? So I think we already answered all the questions on this problem. Any questions on this guy? Okay. So let's do one more. I haven't made up a homework assignment yet, but I'll get one made up for you, I promise. We'll do one more and then we'll move on to the next section, which is related rates. And that I do have a handout for you. So now instead of a ball being thrown up in the air, coming back down, we have an object that's moving back and forth on a real number line, right? You can think of it as on a straight road. Okay. velocity traveling along the number line has its position, S of t, given by that function. Okay. So S of t, the position is in meters, and t is in time. Okay. So let me give you a visual of what's happening. You can always think of this as a straight road if you want to. So here's our number line. 0 at the origin. 1, 2, 3, 4, 5, -1, -2, -3, -4. And this number line applies to the position function S of t. It's not a time line. This is a position line. Okay? Tells you where you're at on the road. Right? At time t. Okay? Now, from our function up here, you'll notice that at time 0, right, t equals 0, S of 0 is equal to 0. S of 1 is equal to, you can check my math, okay? I'm not going to write the arithmetic on the board. You can check my math, and if you get something else, speak up. Okay? So at t equals 1, we're at position -1.75. At t equals 2, we're at position -4. At t equals 3, we're at position 2.25. And lastly, at position at t equals 4, we're at position 32, okay? Which is way out there to the right, okay? So at t equals 0, this is where we're at the origin, okay? Time t equals 0, we're at the origin. At time t equals 1, we're at -1.75 on the number line, okay? So the implication is we move from here to here, right? In the first second, okay? And at t equals 2, we're at -4, which is out here. So the implication is from t equals 1 and 2, we move from here to here. Okay. And at t equals 3, we're at 2 1/4, which is right here. So the implication is from t equals 2 to t equals 3, right? We move from here to there. Okay. So this number line gives us the position, the location of the object at time t. Okay. It's not a timeline. Okay. I want to emphasize that it's not a timeline. Okay. So in A, we're going to find the object's velocity, acceleration, and speed. Well, the velocity is the rate of change of the position function, right? So this is just a polynomial on the right-hand side, right? Differentiated term by term. The derivative of 1/4 t to the 4th using the power rule is equal to t cubed. And the derivative of -2t squared is -4t. So that's the velocity function. The acceleration function is the derivative of the velocity function, right? And the derivative t cubed is 3t squared, and the derivative of -4t is -4. And the speed is the absolute value of the velocity, right? The absolute value of the velocity in this case is equal to the absolute value of t cubed minus 4t. All right. So any questions on that? Nada. Okay. So in B, we want to know when is the object moving in the positive direction. Well, positive directions from left to right, correct? How would we figure that out? What has to be true for it to move in a positive direction? The velocity has to be greater than 0. When the object is moving to the right, the velocity is positive. When the object is moving to the left, the velocity is negative. Okay? Well, the velocity is given by the function t cubed minus 4t. That's a polynomial inequality. Have you ever solved one of those in pre-calculus? The answer is yes. Okay. And so if we factor the polynomial on the left-hand side, you can see we can factor out a t. Okay. And when we factor out the t, and then factor t squared minus 4, we get t plus 2 times t minus 2. So this is a polynomial inequality. So now we gotta find the values of t. I left off one piece of information up here, just so that we're all on the same page. Time doesn't actually begin at 0 in this problem. Time begins at eternity past. Okay? So t can be negative in this problem. All right. So to solve this polynomial inequality, we got to find all the values of t that make the left-hand side greater than 0, right? So, try your memory. Here's the number line for the variable t. Now that number line we draw over here is not the same as this one. This is for the position of the object. This number line over here is for determining the times when the velocity is greater than 0. Okay, so don't confuse the two number lines. Okay? And once you got 0 on one side of the inequality, right, you guys set each of these factors equal to 0. You divide the real number line into intervals. So So those are the three values of t that make the left-hand side equal to 0. So we have -2, 0, and +2. None of those numbers are in the solution set, because they're strictly greater than 0. And now you got to do either the test point method, the table method, or the sign method, determine whether the numbers in each of these four intervals, whether they satisfy the inequality or not. And so I'm going to go through this quickly. I use the sign method. -3 is less than -2. So if I put in -3 in for t, right, this is negative. -3 plus 2 is -1, that's negative. -3 minus 2 is -5, that's negative, right? So we have the product of three negatives, which is negative. And so no number less than -2 makes the left-hand side greater than 0, makes the left-hand side less than 0. Okay. And then if I do the sign method in the second interval, -1, -1 is negative, -1 plus 2 is positive, and -1 minus 2 is negative. So I have negative times positive times negative, which is positive. So all the numbers greater than -2 and less than 0, right? T greater than -2, t less than 0, satisfy this inequality. And so for t greater than -2 and less than 0, the velocity is positive. Okay? And the object is moving to the right. Right? When is the object moving in the positive direction? To the right. Okay? Similarly, you do the same thing from 0 to 2. When you put 1 in for t, you get positive times positive times negative, which is negative. So from t equals 0 to 2, the velocity is negative and the object is moving to the left. Okay. And then lastly, for t greater than 2, you use 3 as a test point. You have positive times positive times positive, which is positive. So for t greater than 2, the velocity is positive and the object is moving to the right. Okay. So math is cumulative. Everything you've learned in your previous pre-calculus and algebra classes gets brought with you to the next class. So the object is moving in the positive direction to the right when the velocity is positive, and that occurs for t greater than -2 and less than 0, and t greater than 2. Okay? That's what we get from our graph here. And so in interval notation, left parentheses, -2, comma 0, right parentheses, union, left parentheses, 2 to infinity. Comes a point where it stops going back and forth and just goes to the right forever. Okay. All right, so we can show this graphically. The behavior of the object. It's called schematic, what we're doing now. Okay. So we know it's moving to the right from t equals -2 to 0, or t greater than minus between for t between minus 2 and 0, and for t greater than 2. Okay. Means it stopped for a moment at t equals minus 2, t equals 0, t equals plus 2. So taking arguing the opposite of that, when is it moving to the left? Well, it has to be from minus infinity, from eternity past, to t equals minus 2. It's moving to the left, right? Well, where is the object at t equals minus 2? Putting in our minus 2 in for t here, we have s of minus 2 is equal to negative 4. So at t equals minus 2, okay, the object is at minus 4 on the number line. Okay. So it started here at eternity past. And at t equals minus 2, it was at minus 4 on the number line. Now I'm drawing a schematic above the number line because I don't want to draw back and forth, back and forth, back and forth on top of each other number line. So I'm putting it above the number line. Okay. So from eternity past to t equals minus 2, right? The motion of the object was from positive infinity up down to minus 4, right, on the number line where it stopped. Okay. Then from minus t equals minus 2 to t equals 0, it moved to the right. And we know from previous work, s of 0 is equal to 0. So here's 0 on the number line. And so from t equals minus 2 to t equals 0, the object moved from minus 4 to 0. Okay. So this is t equals 0. Okay. But then that means that from t equals 0 to 2, the object is moving to the left again. Okay. And where was the object located at t equals 2? It was equal to at minus 4 on the number line. So that's t equals 2. Okay. Now remember, this what I'm drawing here, we would normally draw on top of the number line, but then you can't read the number line. Okay. So in eternity past to t equals minus 2, the object moved from positive infinity to minus 4 on the number line. And then from t equals minus 2 to t equals 0, it moved from minus 4 to 0 on the number line. And then from t equals 2, 0 to t equals 2, it moved from 0 back to minus 4 on the number line. Okay. And then from 2 to infinity, for t equal greater than 2, it moves to the right forever. Okay. The arrows indicate the direction of motion. Okay. All right. So any questions on the motion of this object across time? All right. In C, distance traveled and total distance traveled by the object. Okay? And the first case we're going to do, okay, is from t equals 0 to t equals 2 times the square root of 2. Okay? Well, I did the math, okay? And s of 2 square root of 2, right? The location at 2 times the square root of 2, right? Plugging in 2 times the square root of 2 up here is equal to minus 4. No, not minus 4. It's 0. So if you put 2 root 2 in for t up here, you find that at time 2 root 2, the object is at 0 on the number line, and that's also true at minus 2 root 2. Okay. At minus 2 root 2, it's also at 0 on the number line. Okay. There's certain symmetry to this problem. Okay. All right. So the net distance is the distance from the starting point, difference between the location of the starting point minus the location of the final point. Okay, so in this case, net distance is the location of the object at t equals 2 root 2 minus the location of the object at t equals 0. And at 2 root 2, it's located at 0 on the real number line. And at t equals 0, it's located at 0 on the real number line. And 0 minus 0 is 0. So the net distance traveled, even though it's moved around, it ended up where it started, and so its net distance is 0. It moved the same distance to the left as it did to the right. Now, total distance is actually the distance that the object traveled, even though it ended up in the same place where it started. So to get total distance, you have to use absolute value. Okay? So we're doing net distance from 0 to 2 root 2. Well, here's where it is at t equals 0, right? T equals 0 is at 0 on the real number line. And then from t equals 0 to t equals 2, it moves from 0 to minus 4 on the real number line. And then from t equals 2 to t equals plus 2 root 2, it moves from minus 4 back to 0 on the real number line. Okay. So in short, it went 4 units to the left, and then 4 units to the right, for a total of 8 units. Okay. So mathematically, that's equal to the absolute value of its position at t equals 2 minus its position at t equals 0. Then we add to that the absolute value of its position at 2 root 2 minus its position at t equals 2. And then you substitute, okay? S of 2 is equal to minus 4. S of 0 is 0. S of 2 root 2 is plus 4, or excuse me, 0. And S of 2 is minus 2. Minus 4. Minus 4 minus 0 is negative 4, and the absolute value negative 4 is 4. Zero minus a negative 4 is 4, and the absolute value of 4 is 4. So 8 meters is the total distance traveled, okay? From t equals 0 to t equals 2 root 2. Okay? T equals 0 to t equals 2 root 2. The total distance traveled is 8 meters. Okay. Science. All right, one more. Then you'll have everything you need for the WebAssign homework. So part 2, we're doing from t equals 0 to t equals 3. So the net distance again is equal to its location at t equals 3 minus its location at t equals 0. Well, its location at t equals 3 is equal to 2.25. I already wrote that on the board earlier. Its position at t equals 0 is 0. And so its final resting place is 2.25 meters away from where it started. Okay. Its final resting place is 2.25 meters from where it started. The total distance traveled is equal to the absolute value of S of 2 minus S of 0. So remember, we're going from 0 to 3, right? T equals 0, t equals 3. So we start here at t equals 0, and it's move to the left until t equals 2. So we got to calculate that distance, and then we got to calculate the distance from t equals 2 to t equals 3. And I think I did put that on the board. Yeah, it's 2 1/4. So at t equals 3, this is where it's located. But then we had the absolute value of S of 3 minus S of 2. So this gives us the distance traveled from t equals 0 to t equals 2. And then this gives us the distance from travel from t equals 2 to t equals 3. Well, S of 2 is equal to 4. S of 0 is 0. S of 3 is equal to 2.25. And S of 0 is 0, or S of 2 is 0. That can't be right. It's got to be 4, right? What did I do wrong? Oh.
S of 2 is negative 4.
S of 0 to S of 2. And this should be S of 3 minus S of 2, right?
You wrote S of 2 equals 0 equals 4.
Hold on a second. S of 2 is negative 4, right? S of 2 is -4. Easy, I got confused. Alright, so from t equals 0 to 3, we gotta do t equals 0 to t equals 2, which is s of 2 minus s of 0, and s of 2 is -4, and s of 0 is 0. And then we gotta add to that s of 3 minus s of 2, right? And s of 3 is right here, 2 1/4. So s of 2 is -4. -4 minus 0 is -4, and the absolute value of -4 is 4. 2.25 minus a -4 is 2.25 plus 4, which is 6.25. And the absolute value is 6.25. 6.25. And so the total distance traveled is 10.25 meters. So from t equals 0 to t equals 3, the object just ends up 2.25 meters from where it started, but it traveled a total of 10.25 meters. It ended up 2.25 meters from where it started. S of 2 minus S of 0. And S of 3 minus S of 2. Okay. Any disagreements with my math? Okay. All right, so I'll get you a homework assignment posted on WebAssign. And now we'll go back to the handouts for a couple of sections. I find the next section not quite as challenging as this one. You're fine. All right. More word problems. Okay.
So we're skipping through 0.8?
Yeah.
What's in it out of curiosity?
Did you take free calculus?
I took it here, not with you.
Yeah, but you did take it.
Yeah.
Did you guys do exponential decay
Yes.
and exponential growth?
Yeah.
That's what it's on.
Gotcha.
So we could differentiate those functions and do all kinds of neat stuff, right? But math department says move on, so we move on. Okay. All right. Related rates. Okay. All right. In a related rates problem, so let's just read through this first part together. In a related rates problem, the idea is to compute the rate of change of one quantity in terms of the rate of change of another quantity. So we're going to compute the derivative of one variable in terms of the derivative of another. Okay. The procedure is to find the equation that relates the two quantities, and then use the chain rule to differentiate both sides with respect to time. Okay. So this is Robert Bell's word problem solving strategy. Okay? This is what I do, try to do. Step number 1, draw a good picture. Visualization is very important in mathematics. Okay? If you visualize a problem, it goes a long ways to help solve it. Step number 2, define the variables. What does X represent? What does Y represent? What does Z represent? And so forth. Step number 3, set up the math equation, right? The equation is just a mathematical model describing the problem at hand. And then step number 4, solve the equation. Okay. So an example, we're going to start small and work up. Suppose oil spills from a ruptured tanker and spreads in a circular pattern. If the radius of the oil spill is increasing at the rate of 5 meters per second, how fast is the area of the spill increasing when the radius is 7 meters? So let's draw a good picture. We have an oil spill, and it's spreading out in a circular pattern, right? You know what a circle is. Okay. R is the radius of the circle. Okay. And so as oil spills out, right, from this ruptured tanker, right, the circle gets bigger and bigger, right? The oil circles get bigger and bigger, and the area consequently is getting bigger and bigger and bigger. And you know the area of a circle is given by the formula A is equal to pi r squared, right? The area A is equal to pi times the radius squared. Okay. We're given how fast the radius is increasing in the oil spill, right? The circle. So we can use that information to calculate how fast the area of the oil spill is increasing. Okay. So you're given the radius of the oil spill is increasing at the rate of 5 meters per second. So in mathematical symbolism, the rate of change of the radius with respect to time is equal to 5 meters per second. That's how fast the radius is changing. Okay. To find how fast the area is changing with respect to time, we differentiate both sides with respect to time. So we have the derivative with respect to time of the area A. That has to equal the derivative with respect to time the right-hand side, pi r squared. Okay. So in this particular problem, both area and the area A and the radius r are changing with time, right? They're functions of time. Okay. So notice we're not differentiating A with respect to A. We're not differentiating R with respect to, excuse me, we're not differentiating the radius R with respect to R. Okay. So what we're using is the differentiation. It's like in an implicit differentiation, you had to use the general power rule. Remember, in implicit differentiation, if you had to differentiate y to the 5th power with respect to x, we have to do the general power rule, right? That's equal to 5y to the 4th times the derivative of y with respect to x. Okay. We're doing the same thing here, only we're differentiating with respect to t. Okay. So the derivative of a with respect to time t is dA over dt. On the right-hand side, pi is a multiplicative constant, right? So we just carry that along. And then we have the derivative of r squared with respect to time, t. Well, using the general power rule, right, bring the 2 down in front of the r, and then subtract 1 from the exponent, and then multiply that by the derivative of r with respect to time t, which is dr over dt. Now we can answer the question at hand. If the radius of the oil spill is increasing at the rate of 5 meters per second, how fast is the area of the spill increasing when the radius is 7 meters? So we got to answer, right? So we got to find dA over dt when r is equal to 7 meters. And we know that the radius of the oil spill is increasing at the rate of 5 meters per second already, right? So to find out how fast the area of the oil spill is increasing, when the radius is 7 meters, and the radius is increasing at this rate, we just plug in for r and dr over dt. We have pi times 2 times 7 times 5. Which is equal to 70 times pi. Which is around 210 something. Okay. Remember, this is a rate of change, right? So this is 70 pi what? What are the units? Meters. So it's going to be 70 pi.
Squared.
Right, it's area, right? You gotta be careful, right? It's square meters. Per. Remember, first derivative is like a velocity of speed, right? It's something for something. It's like miles per hour, right? People per year, right? Something for something. So it's 70 pi square meters per second. Does that make sense? Sort of? Yes, sir.
How exactly, again, did we get from derivative of r with respect to t to like 7 times 5? Or...
Oh, well, we're finding, right? The question is, if the radius of the oil spill is increasing at the rate of 5 meters per second, we're given that. How fast is the area of the spill increasing when the radius is 7 meters? Okay. So we're finding out how fast the area is changing when the radius of the oil spill is 7 meters. Okay. And at that point in time, okay, the area of the oil spill is increasing at the rate of 75 square meters per second. Okay. And so all these problems are going to be like this, right? You're going to have an equation that you're familiar with. And you're going to differentiate both sides of the equation with respect to time to get the rate of change of one variable with respect to time using the rate of change of the other variable with respect to time. Okay. So we're actually dealing with 3 variables in these problems, right? In some problems it's 4 variables. Okay. Up to now, right, for today, you're just dealing with 2 variables, x and y. But in problems like this, right, we're dealing with 3 variables, a, r, and t. Okay? And there are some problems where we're going to be dealing with 4 variables, x, y, z, and t. Okay? All right. You guys have had enough for one day, I can tell by we'll finish this hopefully tomorrow. But let's take attendance. Since we have a few minutes. Cameron's here, Laura's here, Leah, Nelson's here, Meredith, Mac, Steve's here, Alex is here, Caroline is here, Lyra is here, Jessica is here, Mary is here, Sahar is here. Julianne is here, Brian is here, Rebecca is here, Laurel is here, Jennifer is here, and Vincent is here. Alright, see you guys tomorrow. Have a good day.